Here's where we get to what I think is by far the most useful thing about Maxima, and that's the ability to define new functions. We've talked about a few functions already, of course. Technically speaking, ratsimp, solve, solve ODE, integrate, differentiate, all of those are functions as far as Maxima is concerned. And we're going to be talking about defining our own functions. This will be incredibly useful for shortcuts. So let's go ahead and start with a simple function, x squared. So we want to say we're just going to define f of x equals x squared. So the way we do that is we say f of x equals x squared. So now I want to go through sort of the anatomy of defining a function. This f right here does not need to be f. I mean, it could be a word. I could define word of x equals x squared. I'm not going to. That'd be weird. But it can be anything, just so long as it doesn't conflict with something that Maxima already has predefined. And this tells us what the arguments are going to be. So this means that we're going to have x as an argument in the function. This semicolon equals means I'm defining a function. That's very important, because otherwise, if you don't put the colon, it's a whole colon, not just a semicolon. If you don't put the colon there, then Maxima will not realize that you're trying to define a function. And the x squared, of course, is the function. So let's go ahead and evaluate that. So we say f of x equals x squared. Now let's try f of 2, which comes out 4. F of a, which comes out a squared. F of x plus 1 gives us x plus 1 quantity squared, or ratsimp. We'll make it x squared plus 2x plus 1. And we can put a lot of really complicated stuff in here, but it doesn't necessarily need to be just what we think of as typical continuous functions. Or even just continuous typical functions, you might say. But it can be something like an if-then statement. So, if-then statements. Okay, so if-then statements are kind of programmy stuff, type of things that you'd see with programs. And they don't actually require, they don't need to be inside functions per se. You can just put an if-then statement directly into the prompt if you want to, but they're most useful as functions. So let's say we want to define a piecewise function. We'll say f of x equals 1 if, oops, that didn't mean to be huge like that, if 0 is less than x, which is less than 1, and 0 otherwise. Sorry, bad mouse writing. It's hard to write with a mouse. Especially words. Numbers are hard enough, but looks like some psychotic wrote it. At any rate, so let's say we want to define this function. So we start out with f of x equals, and now we're defining the function. So I try to think of this as a logical statement rather than as in this form. So I'd say if 0 is less than x and x is less than 1. So that's saying if this is true, if 0 is less than x and x is less than 1, I can't just put 0 less than x less than 1. Maxima didn't recognize that, so you'd have to have these two logical statements joined by and. And of course, or is also a valid logical statement as well. Then, so if 0 is less than x and x is less than 1, then the value of f of x is going to be 1. So that means that if this statement is true, then this will be the value of f of x. But there's another part to an if-then statement, and that's the else part. That means that if this is not true, so if this is true, then this is the value of f of x. But if this is not true, then the following thing that comes after else is going to be the new value, and we're going to say else 0. So if this is not true, then the value of f of x is going to be 0. So let's go ahead and define that. So if 0 is less than x and x is less than 1, then the value is 1. Otherwise, it's going to be 0. Let's go ahead and plot this. You can actually plot this piecewise function. So let's plot f of x, and I'm going to say I'm going to limit the y values, and the reason why is because otherwise it would look very strange. You can kind of, it's my opinion that more often than not it's best to go ahead and redefine the y values, because otherwise it will be zoomed in so much that it'll be hard to see what's going on, or maybe it'll be zoomed out so much that it'll be hard to see what's going on. So now we have a plot of this piecewise function. Now there is kind of an inaccuracy because this should be discontinuous right here. It shouldn't be a line. There shouldn't be this vertical line. These two vertical lines shouldn't be here. This is pretty common for CAS programs. I think it's probably will do it in most of them. I know it would do it if you were to graph this on a TI calculator. The reason why it does this is because the way CAS programs graph is it'll just plots a bunch of points and then connects the dots. So it plotted this point and it plotted this point and it connected those two dots. But the point here is that we have successfully defined a piecewise function. You might be able to change that using some sort of messing with the defaults for Maxima, but it's really not worth the effort. So we're going to go ahead and call this good. So, but there's a little bit more to if-then statements. Actually, there's quite a bit more to if-then statements. We're only going to be scratching the surface of if-then statements. But let's define g of x as if x is equal to yes, then true, else false. So now we can see that the if-then statements do not necessarily need to have numeric values. So we're saying that g of yes will give true. G of no will give false. So what would g of 4 be? G of 4 is also going to be false, because we didn't actually set up a dichotomy where g has to be, the argument for g has to be yes or no. We're just said if g is yes, then the value of g of x is true. If it's not yes, then the value is going to be false. Not yes includes no, it also includes 4, it also includes blah 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 blah. If I wanted to set up a dichotomy where we'd have something else, we'd say we could have, if we wanted to set up a dichotomy, we could have an if-then statement inside an if-then statement. So we could say, instead of false, we could say if x equals yes, then true, else if x equals no, then false, else error. So g of x equals yes, g of no equals false, g of 4 equals error. So this is an if-then statement inside an if-then statement. So this if-then statement is the else condition for the whole if-then statement. So anyway, let's go on beyond if-then statements. Now again, we're only scratching the surface of if-then statements. There's so much more to do than that, but I'm not nearly qualified enough to actually go through all the details of what you can do with an if-then statement. You might want to take a programming class if you want to figure that out. So now, let's talk about for loops. For loops are repeated operations. It will do so let's say we want to do something for we want to do some operation of k. So we want to do f of k, and we want to do it when k is equal to 1. We want to do it when k is equal to 2. We want to do it for all through a predetermined number. So what we can say is that we can use the for loops. Now I think the only way I can think to actually do and to describe what a for loop is to show an example. Let's do an example before we actually define a function. First, let's define what I want to do is set up a for loop that will add all numbers up to a certain number, all positive integers up to a certain number. So first let's set m equal to 0. So if m is 0, now let's do the for loop. Now we start out with for k is equal to 0 through 100, do m defined as m plus k. Okay, so now let me explain exactly what this means, the syntax of the command. This means that I want to do, when k is, first of all, I want to take m, and I want to add k to it when k is 0. So that means 0 plus 0. So for the first iteration, when k is equal to 0, we will do m is already 0, plus, or let's do it this way. We're going to define m as m, so this first m is going to be 0 because m is already 0, but now we're redefining it as 0 plus 0. So now our new m is going to be the same as the one before, it's got to be 0. But now we do the same thing when k is equal to 1. So we have m is equal to, we're going to define m as 0 plus, but now k is 1, so we have plus 1 equals 1. If k is then we do the same thing, but when k is equal to 2. So we say m, we're going to define it as the previous m plus 2 equals 3. So our new m is now 3. And you do this up until you get to 100. And then we're going to find out what what the sum of 0 through 100 is. But of course now it just said done. Now it didn't give us the value of m because that wasn't actually what we asked it to do. We didn't ask it to give the new value of m. We only asked it to define m this way. So now we want to say what is the new m? It's 5050. And if you remember from calculus, the sum of 0 through 100 is 5050. Of course, Maxima has a summation option already. We did it in one of the previous videos. But the point for this is just to see how to deal with for loops. So, how then do we make this into a function? So let me clear all that off. We make this into a function by using what's called the block command. So the block command, so if I say block, what this does is I can do multiple commands inside the block command. It will only show the results of the last command. So I'm going to put all of these three steps into this command. So I'll say first I'll set m equal to 0, comma. Now I'll go to the next command. Now I'll do do the for loop. For k through 100, do m is defined as m plus k, comma. And now we want to say show us what m is. So now we're done with the block command. It's going to do this, and it's going to do it. It's going to do all three of these different commands. It's only going to show us the results from the last command. So that gives us 5050. Now let's turn this into a function, something that's more generic that we can use for any number. So we'll say that sum of x, I'm going to use just x, s of x, and the reason why is just because we already have a sum command in Maxima. So now it's going to be defined as block m is equal to 0, then for k 0 through x, do m plus k, and now show us what m is. So now we have the sum command set up, so we can do sum of 100, 5050, sum of 25, 325. Let's do sum of 2. Sum of 2, 3. That makes sense. Sum of 3, 6. Again, that makes sense. So now we have the summation command set up as a for loop, and it looks like it works just fine. Now, there's one more thing about the for loop that's worth mentioning, and that is that it doesn't necessarily need to be in a what's what I'm looking for. It doesn't necessarily need to be a just 1. Like k doesn't have to always increase by just 1. It can increase by 0.5 or by 0.2. So let's say we have this list. We're going to say L is the list, the single element list 0. Now let's set up this for loop for k 1 through 10 do append. We want to redefine L as append L k. So this is going to, for every, it's going to it's going to add elements to L, and we can see that L is going to be elements 0 through 10. On the other hand, what if we didn't want to do just the elements 0 through 10? What if we wanted to include all the elements in between? So we just do k is 1 through 10 step 0.5. Now let's go ahead and redefine L so we don't get a huge list. And let's go ahead and include 0.5 because this for loop starts at 0.1. So now we can do this step 0.5, and we now have all of the elements 0.5, 1.5, 2.5, all the elements, all the numbers through 10 that are mod 0.5, I guess you might say. That didn't sound quite right, but it doesn't really matter. At any rate, this demonstrates how you can use the step. There's an argument, maybe there's a word for that, but I don't know what it is. How you can use the step to make your k more refined, you might say. So that concludes everything I had to say about the for loops, but there's one more command worth mentioning. You'll probably use this a lot less often, but if you understand this now, then you'll save the headache I went through to figure it out, and that's the substitute command. So we have substitute command, and substitute is actually right here. But the thing that's important to understand is that when you are defining a function, technically speaking, a function cannot be an argument in a function whenever you're defining it. It can be whenever you're evaluating it. What I mean by that is, let me just go ahead and go through the process that I went through whenever I was trying to figure this out. Let's try to define the forward difference. We're going to write a new function that's going to find the forward difference of f of x. Now, this is the difference operator. If you ever had the difference equations class, the difference operator is going to be f of x. Sorry about that. Okay. So the difference operator is going to be take a function, and it's going to take f of x plus 1 into the function and then subtract f of x out of it. So this is the difference operator. So let's try, and I'm going to say ahead of time, this will not work. This will get an error, and this is what made me confused whenever I tried to do. I don't think this is what I was doing specifically, but this is the type of thing I was trying to do. So let's say I want to say forward difference. I want to define forward difference of f of x. So I'd say, well, that's simple enough. I do f of x plus 1 minus f of x. And now it gives me an error. The reason why is because whenever you're defining a function, you can't use a function as an argument. You can, whenever you are evaluating a function, put f of x into it, but not while you're defining it. So instead, we use the substitute command. So now let's do the new way, the correct way to do it. Now I'm no longer have f of x, I just have f, because f is technically speaking a variable. So I'm now treating f no longer as a function, but as an expression. And technically speaking, in some kind of sense, that's kind of what a function is, an expression. So now, instead of saying f of x plus 1, I'm going to use the substitute command. And the way I'm going to do that, I'm going to say substitute f of x plus 1 in for x in the expression f. So that means that this substitute right here is this right here. This is saying that wherever you take the function, take the expression f, wherever you find an x, replace it with an x plus 1. So now that is substitute x plus 1 in for x in f. And now, to finish the command, I subtract off f of x. F of x, of course, is just an expression f, as far as Maxima is concerned. So now I can define this function correctly. So now I have forward difference of f equals all this stuff. So now let's go ahead and try it. Forward diff of x. This should give us just 1. And it does. Forward difference of x squared. X plus 1 quantity squared minus x squared. And you can see that that's what that's going to be. And we could also simplify this to 2x plus 1. And that is how you would define a forward difference, or to put it more generically, or more generally, I guess is what I meant to say, is that is how you would define a function whose arguments are functions. You treat them as expressions rather than functions. Well, that concludes this video. I will see you in the next video.